Hello students, welcome to this lecture number 3 on the chemical equilibrium. In this lecture, we are going to discuss the very important thing in this chemical equilibrium chapter, that is the law of chemical equilibrium and the equilibrium constant. Both are very important to understand. So you must see this video till this end. So let us write the heading of this today's video, that is law of equilibrium. And equilibrium constant. Equilibrium constant. This is K.K. Mukherjee in Science with Mukherjee Sir YouTube channel. First, let us understand what we mean by the equilibrium mixture. Equilibrium mixture is basically the mixture of the reactant and the product at the time of equilibrium. And that is, it is very much important at this point when we reach the equilibrium of the reaction to know the concentration of the equilibrium mixture. And to know this composition of the equilibrium mixture, we need to know the relationship between the concentration of the reactant and the concentration of the product. And to know this relationship, we have been taken one very general equations. This is the reactant A and B, and it will going to produce the C and D. And it is a balanced equation. Two scientists, that is Goldberg and Oege, in the year 1868, they proposed a relationship between the concentration of the reactants and the product, and this is called the equilibrium equation. Equilibrium equation. And this relationship is like this, that this is the equilibrium constant and it is related to the concentration of the product, that is the C and D, square bracket this C and D, here the square bracket in the C and D is the concentration of the time of the equilibrium, concentration of the product, concentration of product at the time of equilibrium. That is why it has been given a equilibrium notation to give a suffix. And here A and B equilibrium in the square bracket is the concentration of the reactant. Concentration of reactant. So this is called the equilibrium equation, and there is two terms in this equation. That is, one is this is called the equilibrium constant, very important thing, equilibrium constant. Equilibrium constant, and it is equilibrium expression. In the expression, you can see in the numerator there is the product of the concentration of the reactions product, that is C and D reaction product concentration, and in the denominator it is A and B, the concentration of the reactant A and B, and this is called the equilibrium equation. And this equation also called, there is another name of this equation, this is called the law of mass action. This is called also law of mass action. Law of mass action. This is also called law of mass action because at the ancient time, early days, the concentration is termed as the active mass, and in this way it has been told, it has been considered, it has been another name that is given, that the law of mass action. So you understand the equilibrium equation, and it is the equilibrium constant expression, and in the left hand side Kc is the equilibrium constant. Now two scientists, what they have done, they made some extensive studies to find out the actual expression of the equilibrium expression. For that, he have taken one reactions, that is hydrogen and iodine in a concealed tube at, that is, you can see there is 1 mole of hydrogen and 1 mole of iodine as produced, and this reaction has been carried out in a closed vessel at the temperature 731 Kelvin, and he has taken the he has taken 6 observations, 1, 2, 3 and 4 and 5 and 6 observations. In this observation, in the 1 to 4, the initial, he has taken the hydrogen and iodine with different concentrations, and it has been left for the reaction will achieve, reaction will go to the equilibrium point, and at this equilibrium point he has collected the data for the with the reference with the respective initial concentration. So here the initial, you can write initial material, that initial reactant is hydrogen and iodide, the 4 of this experiment. In the 5 and 6 experiment, he has taken the hydrogen iodide as a starting material, and with this starting material he leaves this reaction to proceed in the reverse direction, and ultimately it will reach to equilibrium, and at that time he has collected the data of this concentration of the reactant and product at the equilibrium. So this is how he has made the experiment. Now question is how to make the actual expression of the equilibrium constant. Experiment, he has collected the data of the concentration of the reactant and product at the equilibrium. Now he has made permutation and combination of the expression of this equilibrium constant, and he put all those value in that expression. That is, first expression he has taken Kc is equal to hydrogen iodide, concentration of the hydrogen iodide at the equilibrium. We are give a EQ model, this is equilibrium, concentration at the equilibrium time, and then he has put H2, concentration of H2 and concentration of I2 at the equilibrium. When he put all this value, the concentration value at this expression, he is found that it is far from constant. It is not constant. Far from constant. It is not constant. Right? But if he put this value in this expression, and he put this value in this expression, what he observed all the time, all the 6 cases, it is become a constant. So what is the difference between two expressions? It is basically the power of the concentrations term. Here hydrogen iodide have the power is 2. Here hydrogen has a power 1 and iodine is a power 1. And this comes from this equation, that is your balanced equation that we have already been acquainted with, that is hydrogen iodide 2HI. This is a stoichiometry. This is a stoichiometry coefficient of this balance equation, and that is here putting here, and it will give the concentration. And this is, we can say this expression, we can say the equilibrium constant. Equilibrium constant for this reaction. For this reaction, the equilibrium constant is this. You can write equilibrium constant is this. So we now understand how the equilibrium constant has been derived, has been deduced from this different experiment, and this has been directly correlation with the stoichiometric coefficient of the balanced equation that we can see for this equation. Okay, so here the law of chemical equilibrium comes forth, that is, right, we have to write this at a given temperature. This is the law of chemical equilibrium. At a given temperature, you have to write given temperature. This is very, very important. Try to understand. At a given temperature, the product So this is the law of chemical equilibrium. At a given temperature, the product of the concentration of the reaction product of the concentration of the reactant product, here is only product is there, so this is HI. Then product of the reaction raised to the power of the stoichiometric coefficient of the balance equation divided by the product of reaction concentration. This is reaction concentration and this is our product raised to the power of the individual stoichiometry is constant. This is called the law of chemical equilibrium, or we can say law of equilibrium. This is very, very important thing that you can see. That is the product, this reaction first in the numerator, that will be the concentration of the product raised to the power the stoichiometry of this reaction, balanced reaction, and it is divided by the product of the reactant concentrations. So this is called the law of chemical equilibrium. Law of chemical equilibrium is this. At a given temperature, the product of the concentration of the reaction product raised to the power of the stoichiometry of the coefficient of the balanced equation divided by the product reactant concentration raised to the power of the individual stoichiometry is constant. So for a particular reaction, general reaction, let us try to understand the equilibrium expressions. let us write the equilibrium expression for this general reaction. So we can write Kc is the product concentration. Here product is C and D. Its concentration is been given by a square bracket, and it has the part, the stoichiometry. Stoichiometry is small c into D. D is another product and its stoichiometry is small d, given by, that is divided by the reactant, concentration of the reactant. It is given by this A, and stoichiometry is small a, and it is given by this. This is the equilibrium expression for equilibrium constant expression for this balance equation. So we can understand how we can able to establish, how you can able to draw equilibrium equations, equilibrium constant expressions for a particular equations. So here another equations that we can have. Before that, we want to go to the type of equilibrium constant. There are basically two types of equilibrium constant. Now let us understand the type of equilibrium constant. Equilibrium constant. That is one type that we have already discussed. It is here the concentration term. This is the mole per liter. This is the Kc where concentration is expressed in mole per liter. Mole per liter. And another thing, that is Kp, that is where the instead of concentration, what we will do, we will concentrate on the partial pressure of the, in case of gases, that is much more applicable, that is the partial pressure of the gases. So this concentration that we will discuss in the this Kp term, that is a equilibrium constant term in terms of this partial pressure, we will discuss in the next video, in the video number 4, that how we can able to draw a relationship between the Kp and Kc. And now units of, what will be the unit of Kc, that you can see we are expressing the concentration as mole per liter, and it is C plus D minus A plus B. So you can see the units of the Kc, that depends on the reaction itself and its stoichiometry of the balance equation. For this reaction, that is H2 plus I2 is equal to 2HI. In this case, you can see the unit of Kc, that will be here C plus D and A plus B, that is same. Here C plus D 2 and A plus D is 2. So Kc will be your dimensionless. So no dimension of the Kc. For this reaction, suppose N2O4 and 2NO2. For these reactions, the unit of Kc will be the mole per liter. So Kc is not, unit of the equilibrium constant is not fixed. It is sometimes dimensionless or sometimes it has some dimension. But when we express this Kc in terms of your standard, in the standard state of the units, then it will become again a dimensionless. So that is, you can understand this type of equilibrium and the equilibrium expression of the equilibrium constant. Now there are something, suppose the reaction is going on This is the reaction, and this equilibrium constant we know, we can write concentration of. So here what is there you need to understand that this EQ suffix you do not have to put, you can omit this. So I am writing that directly that Hi square, there is concentration of H2 and concentration of I2. Okay, so this is the Kc. Suppose what will be the equilibrium constant for this reverse reaction? For this reverse reaction, equilibrium constant is what is? Suppose this is Kc1. So what will be this? Then this will be H2 product. In that time, in this reverse reaction, product will be this H2Y2 and is reactant will be this. So you can see what is the relation between these two. Between these two, the relation is, you can see Kc is 1 by Kc dash is 1 by Kc. So you can see here the equilibrium constant. We can write this very important note that the equilibrium constant of the reverse reaction is the inverse of the forward reaction. That we can write. Very important thing to understand. Forward reaction. In the forward reaction, if the equilibrium constant is Kc, then in the reverse reaction it will be 1 by Kc. Another thing, suppose we have changed the stoichiometry by multiplying some factors throughout this equation, then what will be, and these changes will be affected the Kc also. As for example, you can see this. This is again the reaction we have taken. In this reaction, we have multiplied a factor both sides of the equation by half, then it will be becoming this. So now the Kc dash, it will be, you can see, what will be this? This is the Hi divided by H2 and I2. Okay. Now you can calculate that this will be the half. So which is you are giving the multiplying this half. So Kc will be half, square root. Kc will be square root of Kc dash will be square root of the Kc. Suppose we add some n. Some factor n is multiplied by both the, then we can write Kc dash will be Kc to the power n. So whatever factor we are multiplying both the sides, that will comes to the your equilibrium constant term. So we can see this. This is a very important thing in the many numericals. You can have to remember this also, right? So that is all for today's video, today's lecture. In the today's lecture, we have covered the very important part, that is law of chemical equilibrium and the equilibrium constant, and we also know now how to express the equilibrium expression of the equilibrium constant for the different reactions, and whenever we have to mention the equilibrium constant, because it is dependent on the stoichiometry of this balanced equation, so we must mention the equation also. That is all for today's video. If you like this video, you can share this to your friends. Thank you very much for watching. All the best.